once you do the button pushing. You just go 1 minus binom PDF, binom CDF and do that. All right. The almost to the last topic here. The mean and standard deviation and the variance of a binomially distributed random variable. All right, we're not going to go through the derivation. It's above and beyond the scope of the course. So just take this as a fact value. The mean of a binomial distribution is n times p. It's just that easy. The variance is n times p times 1 minus p, and the standard deviation is the square root of all of that. So again, once you have n, p, and x, or n and p, like I said earlier, the binomial distribution is fully characterized when you know n and p, and you know everything about the distribution. So going back to the president approval rating, let's just recall that we said that the probability of a success for the president, the probability was 0.53, and our sample size was 5. So we can compute the mean as 5 times 0.53, and when you do that we get 2.65. So again, what this means is if you go out and sample 5 people a large number of times, you will find that on average 2.65 people will agree with the president, how he's handling the issues. If we take a look at the snake issue, the fear issue, remember the probability that somebody is afraid of snakes was 0.36, and we were using sample sizes of 10. So again, if we wanted to compute the mean, remember the mean is going to be 0.36 times 10, which is equal to 3.6. So let's just remember what that means. If we sample 5 adult Americans, 10 Americans a large number of times, we will find that on average 3.6 of them are going to be afraid of snakes, or at least list that as their number 1 fear. Okay. The standard deviation is going to be n times p times 1 minus p. So for the president, sigma squared then is equal to n, which is 5, p, which is 0.53, and then 1 minus 0.53. So when we compute that, we get 0.2445. And over here for the fears, sigma squared, again n is 10, p was 0.36, and then 1 minus 0.36. And if you compute that, you should come up with 2.304. So computing the mean and the variance, again, you have to recognize that it's binomially distributed, and boom, it's that easy. And this mean comes about from using the x times p of x and then adding them all up. But we're not going to go through all of that. And then finally, there's one last thing, is the shape of distributions. The binomial distribution does have some shapes to it. And the idea is, if notice that this distribution, would you agree, is skewed right? Yes. And this distribution is symmetric, and this distribution is left skewed. And the probability for a success is 0.25. Now, let's just see if this makes sense. If the probability of a success is 0.25, then wouldn't it make sense then, if we chose n as 10, that these lower bounds, that these lower numbers here will have a higher probability of actualizing, if you will? But as n gets closer to 10, the probability becomes smaller to get the higher numbers. That was a question. Does it make sense? If you choose 10 and you have a small probability, that means that the probability, since the probability is small, you would actually see smaller numbers, 1, 2, 3, 4, with a higher percentage of occurrence than larger numbers, 8, 9, and 10. Does that make sense? And then over here, as I increase the probability to 0.75, then wouldn't it make sense that if I had 10, wouldn't it make sense if I had 10 with a larger probability that the realizations of the higher numbers would have a higher probability than the realizations of the lower numbers? And notice what happens when p is 0.5. It's a symmetric distribution. So the bottom line is this. If the probability is less than 0.5, you know the shape of the distribution is going to be. If the probability of a success is less than 0.5, then you know the shape of the distribution is going to be. Man, the pictures are right here. You guys are killing me here. Let's try it one last time. If the probability of a success is less than 0.5, then you know the shape of the distribution is going to be right skewed. Not left skewed, not symmetric, right skewed. When the probability is 0.5, symmetric or bell-shaped. And when the probability of a success is greater than 0.5, then the shape of the distribution is going to be left skewed. Okay? That concludes our discussion on the binomial distribution.